Hopefully it won't be too long. Chemistry paper two, there's not that many topics, but there will be some paper one topics they're gonna add in. So at the end of the video, there should be some paper one topics. You're gonna see them again. You just get a little refresh, a little reminder because it will come up in this paper as well. Like if you see this question here, like if you don't know about like ionic bonding, you're finished. You can't answer it. We're gonna start off with group one. So you guys should know what the group number means. First of all, that's pretty important. So your group number means how many electrons you have in the outer shell. For example, everything here, so lithium, sodium, potassium, all of them have one electron on the outer shell. Same with like group two, right? Beryllium, magnesium, all these ones, they have two electrons in the outer shell. Your period number, so like how far down it goes, that tells you how many shells it has. For example, I know that sodium is in the third period, right? That's one, two, three. That means it has three shells. So it should end up being 2, 8, 1. So three shells and then one electron in the outer shell. That's like, yeah. Cool? Cool. But honestly, you don't need to worry about group 2 or 3 or 4 or 5 or 6. The only ones you care about is 1, 7, and 0. That's the only ones we'll be talking about. And naturally, we should start with, group 1, right? I think that makes no sense. 1 comes, like, whatever. The point is, group 1, what you need to know. Firstly, they are very soft and they're very like low melting point. They're not like some strong, obviously they're metals, but they're not strong metals. For example, lithium, all the stuff here, you can cut these metals with a knife, like bar. But when it comes to the reactivity though, that's the most important thing. Group one and group seven, very, very reactive. And you'll see that in this little experiment kind of thing over here, when you drop the thing in water. So if you have any group of metal and you put it in water, you should see a reaction happening. Hopefully you guys have done this in school before. I don't know if you guys have the resources for that, but when you put a group of metal in water, it will start fizzing up. You need to know the equation for this. So any group one metal plus water makes the metal hydroxide and hydrogen gas. So you should see hydrogen gas like coming out of it. Yeah. So it'll be pretty like it'll be like. I mean, if you've seen it, you know what I'm talking about. And it's like, but yeah, you need to know this equation. So metal plus water makes metal hydroxide. But if you drop sodium in it, it goes like a little bit. But if you're dropping like, let's say francium in it, it'll be like. So what I was telling you is, as you go down group one, they get more and more reactive. So the ones on the top are a little bit reactive. The ones at the bottom, very, very reactive. As a little recap from ionic bonding, every atom wants to have a full outer shell. For example, sodium has like one measly electron on the outer shell. So sodium wants to lose this. So it now has a complete full outer shell. It has 8 over here. Similarly, chlorine wants a full outer shell. Anything wants a full outer shell. So chlorine will have to gain an electron to get a full outer shell. You're going to need to be able to explain that trend as well. And this is potentially a 6-mark question. So again, we should know that anything in group 1 has 1 electron on the outer shell. When they react though, they need to be giving away that electron. This is similar to the ionic bonding topic, so your metal should be giving away the electron. If you look at lithium here, it's a very small atom compared to sodium and potassium. This means that the attraction between the nucleus and the outer electron is very strong because they're very close to each other. But you can see with potassium, the nucleus and the outer electron are very far away from each other. So you want to say lithium or just any group of metal wants to give away an electron to react. As you go down the group, the atom gets larger. This means that the outer electron will be further away from the nucleus, which means the attraction will be weaker. Therefore, it is a lot easier for you to lose that electron. Like potassium, because the outer electron is so far away from the nucleus, like it'd be easy for it to get lost. Compared to lithium, it's so close to the nucleus, it'd be very hard for you to take the electron away from it. Now looking at group 7, again, the 3 main ones you need to know are chlorine, bromine, and iodine. One thing that's kind of important about group 7 is anytime you write like the chemical formula for them, you should always put like a 2 next to it, like CO2 or Br2 or F2, and in this case iodine, so I2. You should always have like a 2 with them. You just need to know firstly what they look like. So chlorine is a yellow gas, bromine is a red liquid, iodine is a grey solid. And this kind of tells you something, right? It's going from gas, liquid, solid. So as you go down the group, the melting point should increase. So melting point increases as you go down the group. That's it. You must also know the test for chlorine. So it should bleach litmus paper, going from blue to white. Don't remember that red part. So it bleaches blue litmus paper, so it turns it white. You can say I don't know, bleaches it white, or you can just write it bleaches it. That's fine. Now, group 7 also has a trend in their reactivity as well. It's similar to the group 1, but it's going to be acting in the opposite way. So as you go down the group, it actually gets less reactive. So again, we need to be able to explain that in a six marky kind of way. So again, chlorine has 7 electrons in the outer shell. It only wants to just gain one. So before it was trying to lose an electron, this time we're trying to gain an electron. As you go down the group, the atom gets bigger and bigger. The outer electrons get further away from the nucleus. Weaker attraction between the outer electron and nucleus. So it's harder for it to gain a new one. So in this case, chlorine is the best at gaining an electron because, it's the most attraction, right? Because it's got the shortest distance. Iodine, very weak attraction. So as you go down the group, they get less reactive. So group 1, you get more reactive as you go down the group, but then group 7, you get less reactive. I like the metals, like remember the reactivity series stuff from before? Similarly, group 7 has that as well. So if I have chlorine, which is more reactive than bromine, it will displace it. And we can see here these examples. So potassium bromide, if I react it with chlorine, you can see the chlorine displaces the bromide. Or if I have potassium iodide, chlorine and bromine can both displace it because they are more reactive. But if you see potassium chloride, none of them can displace it because chlorine is the most reactive, so they cannot displace it. And here's like a written example. So if I had bromine and I reacted it with potassium iodide, because bromine is higher up in the group than iodine, I know that bromine is more reactive. So, yep, the bromine should displace it. So it becomes potassium bromide, and iodine is by itself. It got kicked out. And if you can't tell what a group 7 element looks like, if anything ends in ene, like bromine or iodine, like it will be a group 7 element, also known as halogen. You can say group 7 element, halogen, whatever you feel like saying, it's your life. And lastly, we have group 0, also known as the noble gases. If you remember group 1, they were very reactive, right? Because all they had to do was lose one electron, and then group 7, they were trying to gain an electron to get their full hour shell, and they were very reactive as well. Group 0, they already have a full hour shell, they don't care. So they are unreactive. They don't really react because they already have a full hour shell. So they don't need to do any of that weird stuff with losing or gaining electrons. So we're going to move on to rate of reaction. And the main thing is collision theory. So collision theory explains how a reaction actually takes place. So for a reaction to take place, the reactant particles must collide with each other with enough energy. So just that, right? So they need to collide with each other with enough energy. So we're going to look at some things that affect the rate of reaction, and you have to explain, for example, increased temperature. Why would that increase rate of reaction? You always need to link it with collision theory. It always needs to make more collisions happen with enough energy. Like that's the most important thing. Just so again, just focus. This won't be like 2 minutes, but it's still kind of important. Increase in concentration increases rate of reaction. Again, concentration just means having more particles. So you have to again always link anything with collision theory. So more particles means more collisions, which means more reactions. Increase in temperature will also increase your rate of reaction. Again, why? You always need to be able to explain it and link it to the collision theory. This is actually a bit of a unique one because there are 2 reasons why it increases rate of reaction. So firstly, the particles will be moving faster, therefore they're more likely to collide. Secondly, if you increase temperature, they will have more energy. And if you remember what collision theory was, they need to collide with enough energy. So you need to say if there's more temperature, more of the particles will have enough energy for there to be a reaction. And lastly, increasing surface area should increase your rate of reaction. And this is because more of the reactant will be in contact with each other. So you can see in this first picture, there's one big fat reactant, right? But in the second picture, you see how they cut it up into pieces. So more of the reactant particles were in contact with each other. Yeah, so again, increased surface area means more reactant particles in contact, therefore more collisions. Again, always link it to collisions. If you're not mentioning collisions in a rate reaction question, you're finished. It's over. Your life is finished. I'm going to say it again because it's just that important. For a reaction to take place, the reactant particles must collide with enough energy. That, like, enough energy is known as activation energy. So activation energy is the energy that you require to do a reaction. A catalyst is something that can increase rate of reaction. I think you guys probably have heard of that before, but you also need to know how it works. So you need to say a catalyst will provide an alternate pathway for the reaction that has a lower activation energy. So you can see here in the diagram, here's that purple line is the normal activation energy. The red one is a new activation energy after you use a catalyst. So using a catalyst will lower your activation energy, which means your reaction will happen faster. There are two ways of telling if a reaction is happening. One would be if there's like a color change, and two would be seeing what's being produced. Like if you look in the case of this experiment here, they're reacting a hydrochloric acid with calcium carbonate, like whatever. That doesn't really matter. The main thing is you can see these gas bubbles being produced. That's telling you the reaction's happening. So if you're trying to measure, for example, the rate of reaction, you can measure how much volume is being made per second. So you like time it and then see how much volume of gas is being produced. And you can see here again in this diagram, you can get the volume of the gas just by checking your apparatus, just looking at it. This specific experiment is trying to see how does rate of reaction get affected by surface area. So as we said before, more surface area should mean a faster rate of reaction. So first you'd use calcium carbonate chips to begin with. But then when you repeat it, maybe you want to use a powder. So the more chopped up something is, the more surface area it has. So you should see a larger rate of reaction when you're using more chopped up pieces. And here's the example for color change. So again, before this reaction, initially it was a transparent solution. So if you're looking at it from above, you should be able to see this black cross under your flask. But after a while, it should change color. And at a certain point, you can't see through anymore. So it's not transparent anymore. So you will not be able to see the cross anymore. So you have to time how long it takes for you to not be able to see the cross anymore. And that's how you get your rate of reaction. In the case of this experiment, we would keep changing the concentration of sodium thiosulfate. And again, if you were paying attention earlier, you should know more concentration means a faster rate of reaction. So you'll keep changing the concentration. So the more concentrated this is, hopefully, the quicker it will take for it to become like opaque, which means like not transparent anymore. The results should generally look something like this. So you'll see as time goes on, more product is being released. The way to find the rate of reaction, so how fast the reaction is going, the whole point of this topic is you want to find the point that's asking for. Let's say it said 5 seconds. You have to draw a tangent line. If you don't have to do that, then again, here's a picture. So you see, you have to line up your ruler with that point here. It has to only touch that point. It can't touch any part of the curve, just that point here. So once you've lined it up, you then need to draw a line going along this. So a line, just like this, a straight line. So that's your tangent at that point. And lastly, you need to find a gradient of this tangent. And again, if some of you guys aren't that good at maths, to find a gradient is a change in y over change in x. So pick two random points and then do change in y over change in x, just like that. An exothermic reaction is a reaction that releases energy. You can tell it's exothermic because your thermometer should go up. So like the temperature of your solution should increase because energy is being released. If it was endothermic, meaning taking in energy, your thermometer will go down so that the temperature will go down. Again, endothermic, you're taking in energy, so your thermometer, so your temperature will go down. Exothermic, you're releasing energy, your temperature should go up. In endothermic reactions, we take in energy so we can break bonds. That's it. So we need the energy to break bonds. In an exothermic reaction, you're releasing energy by making new bonds. So making a bond should release energy. And here's the most common question they can ask you when it comes to endothermic, exothermic reactions. It'll be like 4 marks. So if you can't do it, then you're just throwing away 4 marks for no reason. So they give you a table here, and this gives you the energy of each bond. As you can see in the original equation, with H2, so a H2 just means like a H and another H. So if you look at a table, that's got a value of 436. So we start with 436. Again, Cl2 is next, right? So that's over here. So ClCl, that is 243. So you want to add those up. So this is for the left side. So you add those two up, and you're done with that side. Now if you look at the right side of the equation, the products, we have two HCl's. So HCl's down here is 432. So we do 2 times 432. This is annoying to type, but yeah. So once you have the left side added up and you calculate the right side, you have to do this original number on the left minus the number on the right, and that will leave you with your answer. If your answer is positive, it's an endothermic reaction. Because we endothermic, we took an energy, yay, positive, that's good. Exothermic, you're losing energy, so it should be negative, like you're releasing the energy. In this case, if we add up the left side, we should get 679. The right side, so 2 times 432, should give you 864. So if we were to minus, so 679, take away 864, you'll just be left with negative 185. So this is an exothermic reaction, and we know this because it's negative. And the last thing you need to know about energy is these reaction profile diagrams. So they'll tell you if a reaction is exothermic or endothermic. And again, just as a reminder, exothermic means we're losing energy, we're releasing it. So if you see the diagram here, you start off at a high energy and you end up at a low energy in your products. Again, endothermic, you start at low energy, but you take in energy, so it should end up being higher. This middle part where it kind of goes up first, that happens for both of them, and that's called the activation energy. So the reason why it has to go up this high is because it needs to meet the activation energy. And again, as a reminder, activation energy is the energy required for the reaction to actually happen. And a catalyst should lower the activation energy. So if you look at the first reaction profile, if I was to use a catalyst, it will end up looking more like this. So the activation energy will be lower, so you require less activation energy. Again, activation energy, important thing, you need it to do the reaction, and it's this hump that you can see on both of them. Because of the very high pressure, deep underground, your dead animals and plants should turn into crude oil. But what is crude oil? Crude oil is a mixture of hydrocarbons. That's all it is. Hydrocarbons are compounds that are made of only hydrogen and carbon. So crude oil is a mixture of a bunch of different hydrocarbons. We need to be able to separate this crude oil, right? Because it's a mixture of hydrocarbons. But what if we just want a specific one, like gasoline or fuel? We don't want a mixture of all of them. So what you'll do is you heat up your crude oil until it turns to gas and pass it into this machine over here. So it's called a fractionating column, and it's a way of separating things based on their boiling points. The main feature you need to know is as you go up this column, it gets colder and colder. So the ones with a higher boiling point will condense first. So these over here, like diesel, fuel oil, they all condense first. The ones with the low boiling points will condense higher up and get piped off. So fuel oil, for example, these ones will get at the bottom because again they have a high boiling point. The ones with low boiling points will be higher and higher. The ones at the top with the low boiling points, good, we like that. Gasoline, yum. Kerosene, great, we like that. The ones at the bottom, no, we don't like that. Not very good. When I say good, I mean how well something can be used as a fuel. So gasoline and kerosene are very good fuels. The ones at the bottom, like bitumen over here, very bad fuel. We cannot use it. Here is an example of some hydrocarbons. So methane, ethane, propane, butane, pentane. These are known as alkanes because they all share a general formula. The main thing you need to know is as your alkanes get larger and larger, their boiling points get higher and higher. And again, if you remember back in that diagram, the ones with the higher boiling points will condense first. So octane will end up like lower in the fractionating column, like it'll condense earlier, whereas methane will condense very high up. So the ones that condense at the bottom are the heaviest hydrocarbons. So we've established that hydrocarbons can be used as fuels, but how do we actually use them? Like, you don't like eat it, right? You have to actually do something to it. So you need to burn hydrocarbons in order to use them. This is known as combustion, and here's the chemical equation for it right here. So it's a fuel plus oxygen makes carbon dioxide and water. In this case, we're using C3H8. This is propane. But again, it doesn't really matter. Any hydrocarbon will work. And if you react with oxygen, it makes carbon dioxide and water. And this is known as combustion, and it's how you produce energy using a fuel. More specifically, this is called complete combustion. This means we have enough oxygen. There's also incomplete combustion, which is when we have very little oxygen. Here are some examples of incomplete combustion. Again, it's very similar, but instead of making carbon dioxide, we only make carbon monoxide, or even just carbon. So with incomplete combustion, instead of making carbon dioxide, you'll make carbon monoxide or carbon. And these are both very bad, very naughty. Carbon monoxide is very toxic and it will kill you if you keep breathing it in. This is because normally your red blood cells should carry oxygen, but instead, carbon monoxide will take its place. So your red blood cells won't be able to carry oxygen anymore because there is, the carbon monoxide there instead. Incomplete combustion is not very good because A, it produces carbon monoxide, which is toxic, and B, it could also produce carbon. And carbon is bad because it can cause breathing problems in people. It's like that black dust that you can see in the air, like coming out of chimneys. Burning hydrocarbons could also lead to acid rain. This is due to nitrogen oxides and sulfur dioxides being produced. But why? Why are they being produced? Blah, blah, blah. Okay. Again, just listen. Stop asking stupid questions. Okay. So inside your fuels, your hydrocarbons, let's say we had ethane, for example. So C2H6. Inside of hydrocarbons or any fuels, there will be sulfur mixed in. So sulfur impurities will be mixed in. So when you burn your fuel, sulfur dioxide is produced. Nitrogen oxides, that's a little bit trickier. In our atmosphere, we have nitrogen gas and oxygen gas. Because a car's engine is so hot, it will cause the nitrogen and oxygen to react together to make nitrogen oxides. So both nitrogen oxides and sulfur dioxide, when they go into the air, they will cause acid rain to rain down. So using hydrocarbons as fuels presents a lot of problems when it comes to pollution. That's why, as an alternative, there's hydrogen fuel as well. So we can use hydrogen as fuel. This is good because it produces a lot of energy and it doesn't really produce any pollution either. But the problem is it's expensive and it's very dangerous to use because it can explode. Lastly, you need to know about cracking. So the larger hydrocarbons are worse. We do not like them. If you remember the diagram from the fractional distillation, they have a high boiling point, meaning they condense at the bottom of that fractionating column, and they are not used as fuels. The smaller hydrocarbons are used as fuels. Cracking is a way of getting large hydrocarbons and breaking them down into smaller ones. So you can see decane breaks down and became octane, which is a better fuel because it's a smaller hydrocarbon. But you can also see a little sneaky ethene over here. So things that end in ene are called alkenes. So we have alkanes and alkenes. Alkenes have double bonds. So you can see this diagram here. There's two lines between C and C. So they have double bonds. This is why alkenes are known as unsaturated. Alkanes are saturated. So again, the definition is saturated means you have single bonds. Unsaturated means you have double bonds. So there are two ways of cracking. One way is catalytic cracking. This is when you vaporize your hydrocarbon and then pass it through a hot catalyst. The other way is steam cracking, which again you vaporize your hydrocarbon and then you mix it with steam. The Earth's early atmosphere was caused by volcanoes. So you should know that all the gases came from these volcanoes. And the main two gases that were in the air were carbon dioxide and water vapor. You need to be able to describe where the carbon dioxide and the water vapor has gone, because obviously now it's not like that. So we're going to begin with the water vapor. So the Earth used to be very, very hot, but then it started to cool down. So when the Earth cooled down, the water vapor in the air condensed to make oceans. So the oceans we have now are from the water vapor. As for carbon dioxide decreasing, there are three different reasons. The first reason is that it dissolved into the oceans. So carbon dioxide dissolved in the water. The second one is they formed sedimentary rocks. And the third thing that happened to carbon dioxide was, plants started to exist. So the plants did photosynthesis, which took the carbon dioxide out of the air. This also led to oxygen increasing. So originally we had very, very little oxygen and a lot of carbon dioxide. But now we have very little carbon dioxide and a lot of oxygen. And it's because of the photosynthesis. So now the atmosphere is 20% oxygen, 80% nitrogen, and then very little of all the other stuff. So you might be thinking, well, how's 80% nitrogen? Where will that come from? But if you actually deep it, nitrogen's been there from the beginning. But the water vapor and the carbon dioxide, they all went like down, up and down, all the stuff. Nitrogen never changed. It stayed at 80% like this entire time. The only thing that changed was carbon dioxide and water vapor went down and oxygen went up. So let's say you have some air in a syringe and you want to find out how much oxygen is in that air. So this is like a little practical kind of thing. So you're going to pump the oxygen into this area in the middle with copper. And then the air will end up in this other syringe. And then you keep pumping it left to right. So pump it from right, then it fills with this one, pump it both ways, keep going until all the oxygen reacts with the copper. Once that's done, the air that you have left should have no oxygen in it because all the oxygen would have reacted with copper. So whatever air you have left, let's say you started with 30 centimeter cubed of air. And after you did this, so you kept pushing it back and forth until it fully reacted with copper, you only have 20 centimeter cubed left of air. This means that 10 centimeter cubed of your air was oxygen because that 10 centimeter cubed reacted with copper. So you only have 10 centimeter cubed of oxygen in your 30 centimeter cubed of air. The rest of it is going to be like nitrogen and all that other stuff. The test for oxygen is if you have a glowing splint, so a splint is like a little bit yellow, red kind of thing. If you put it in the oxygen, it will relight it. So it will set back on fire. So oxygen should relight a glowing splint. Carbon dioxide and methane are known as greenhouse gases. But what does that even mean, right? So this is a diagram showing the greenhouse effect. So normally heat will come from the sun, the earth will absorb it, and then reflect it back out. This is pretty bad because, we're going to freeze to death, right, if we don't have any heat. So the greenhouse effect is around our atmosphere, we have greenhouse gases, and these will cause the heat to deflect back onto Earth. The problem is nowadays we have too many greenhouse gases. So normally having a normal amount is okay because we need it, but having too much means too much heat is being kept inside the Earth, which means the Earth is going to start warming up. And this is known as global warming, and you guys probably heard of that. This is all humans' faults, and this is because we are creating more CO2 by burning fuels. We're creating CO2 when we kill trees, and we create CO2 when we use electricity and those things. Also, methane. Methane comes from animals farting. And because we keep farming animals, we're causing more and more methane to be produced. So that's it for paper two. But I'll leave a link to my paper one video just to go back over the mole stuff because that should come up as well in this paper. So it should be a quick little section. I'll put the timestamp in the comments of that video. Also, I'll be releasing the triple section in like a little bit, maybe in like 10 minutes.